In the first part of our lecture on the fate of the universe, we followed the evolution of our accelerating, expanding universe from the first stars to the end of the local group coalescing into a giant elliptical galaxy. In the same time, the sun will have long since faded into a white dwarf into the long night. The universe is now 1 trillion years old. How far can we carry this evolution forward into the future? And what is the ultimate fate of our expanding universe? When the universe is about 2 trillion years old, the accelerating expansion of the universe will carry all of the galaxies outside of our local supercluster beyond our observable horizon. These galaxies will now be moving away too far for us to be able to see them anymore. The galaxies are beyond our horizon and are too redshifted to be able to see. After a while, even those small handful of galaxies that are just outside what remains of the local group will be out of causal contact with the rest of the universe. Our universe will suddenly be left with only the galaxies around us. The degenerate epoch begins when the universe is at 10 to the 14 years old, 100 trillion years old. This is the time when all star formation will end and the last stars will make the last of the degenerate remnants, white dwarfs, neutron stars, and black holes. The free gas reserves of the universe will have finally been exhausted. The cycle of star birth and death that has been going on since the universe was 500 million years old has finally been broken. Nuclear fusion will cease, and red dwarf stars will burn out as low-mass helium white dwarfs. All of the remaining matter is locked up in black dwarfs, cold neutron stars, and black holes, except for those small, tiny, thin bits of matter that were never formed into stars and still remain as an ever-thinning, ever-colder gas. After the universe is about 10 to the 15 years old, all the planets around all the stars will either have fallen into the remnants of their parent stars or have been ejected into interstellar space by gravitational encounters with other stellar systems. Some planets will spiral in and merge with the remnants of their parent stars over a very long period of time as gravitational radiation slowly but surely bleeds away angular momentum, and the planets will eventually merge with their white dwarfs or neutron stars or black holes at the center of their systems. Others will be disrupted by gravitational encounters and scattered into space, where they will wander until they run into a black hole or find themselves deep and empty and alone in the darkness of space. By the time the universe is 1,000 trillion years old, all of the planetary systems that have formed since the first star systems formed at 500 million years into the Big Bang will have dissolved and gone away. Now we're getting into timescales of 10 to the 19 to 10 to the 20 years. By this time, the galaxies will have all dissolved as stellar remnants escape or fall into the supermassive black holes. Star-star encounters, and later on stellar remnant-remnant encounters, will eventually change the gravitational configuration of a galaxy. This is an exceedingly slow process, and while it is important in part of how galaxies get their shapes today, if allowed to run for a very, very long time, how long? About 10 to the 19 or 10 to the 20 years, eventually the galaxy's contents will begin to interact in a way that causes the galaxies to slowly but surely dissolve. About 90% of the remnants of the galaxies will gain enough energy from their interactions to be able to exceed the escape speed and so escape from their galaxies and go out into the cold of intergalactic space. The remaining 10% will lose energy and fall into the central supermassive black hole, where they will be consumed, briefly shining as their matter falls into the black hole and causing the central black hole to grow larger. The last few quasars, the last few accreting supermassive black holes, will continue to shine through this period as long as there is still matter in some form to accrete. It might be degenerate white dwarf matter, it might even be degenerate neutron matter. As long as there's something to eat, the gravitational energy will be released, and we will see tiny bright flashes of the last emission of light. By the time the universe is between 10 to the 34 and 10 to the 40 years old, matter itself as we understand it will begin to dissolve as protons steadily decay into positrons and photons. Particle models of physics predict that protons are in fact unstable and will eventually decay into positrons and photons. It's basically a two-step process. A proton decays into a positron plus a neutral pion, a heavy particle, and the pion itself is unstable and eventually decays into two gamma-ray photons. The end state is protons turn into positrons plus a pair of gamma-ray photons. Experiments have shown that the proton half-life must be extremely long because we do not observe yet any protons to have decayed in the universe. The half-life currently has a limit of at least 10 to the 36 years, perhaps longer. The actual limit is not well understood because we have not yet seen any evidence of even one proton to have decayed anywhere inside of our giant particle detectors. The Super Kamiokande detector, which we saw in previous lectures as being used to detect solar neutrinos and neutrinos from nearby supernovae, has also been used to try to search for the evidence of proton decay. Some models say it's long, some models say it's short. Those with relatively short decay times have already been ruled out, but long decay times are still in play. But we have an infinite universe. We have literally all the time in the universe to wait. And 10 to the 36 years, if that's the proton half-life, eventually matter will begin to dissolve. All of the matter that is not locked up inside of black holes will begin and complete the process of dissolution when the universe is approximately 10 to the 40 years old. If the half-life is 10 to the 36 years, the first significant proton decays will occur around 10 to the 34, and by 10 to the 40, nearly all of the protons in the universe that have not fallen into black holes will have decayed into positrons and photons. At 10 to the 40 years, with the last dissolution of organized matter, black hole epoch will begin at 10 to the 40 years after all the matter that is not locked up in black holes is dissolved into leptons and photons. After 10 to the 67 years, the remaining stellar mass black holes will have evaporated by emitting Hawking radiation. We met Hawking radiation at the end of our lecture on black holes back in Unit 2. However, Hawking radiation in the present epoch is extremely slow and extremely inefficient. The lifetime of a stellar mass black hole is approximately 10 to the 60 or more years. The universe hasn't been around long enough for black holes to begin to evaporate, certainly not of stellar mass black hole size. But when the universe could be infinitely old, it has all the time it needs, and when the universe gets to be 10 to the 67 years old, nearly all of the stellar mass black holes will have vanished into subatomic particles and photons. After 10 to the 100 years, the very largest supermassive black holes that were once at the centers of their galaxies will begin to evaporate one by one as Hawking radiation erodes them away, and eventually the last black hole in the universe will vanish in a weak flash of gamma rays and subatomic particles. This will mark the end of the epoch of all forms of organized matter in the universe. All that will remain are leptons, electrons and positrons, handfuls of neutrinos, and photons, filling an increasingly dark and disorganized universe. At long last, 10 to the 100 years after the Big Bang, we've reached the end. The final dark epoch will begin when the last black holes will have evaporated. The universe continues to expand, continuing to cool off as the radiation temperature approaches absolute zero. It never gets there because it would take an infinite amount of time, but an infinite amount of time is what an infinitely expanding acceleration universe has to work with. The last matter in the universe is a thin, formless gas of electrons, positrons, and neutrinos. The last light is a few increasingly redshifted photons fading and stretching into longer and longer wavelengths. The final state, in the end, is a cold, dark, and disordered low-energy state. What began in the brilliant flash of the Big Bang and the creation of all the matter and radiation that we see around us will end in a cold, long, dark night of dissolved matter and increasingly redshifted photons.